All right, so what we're going to be taking a look at here today is we're going to be looking at something inside of the divergence theorem. It's actually a kind of problem where we can utilize the divergence theorem to deal with a surface that actually wouldn't normally be dealt with utilizing the divergence theorem. So let's say I have this kind of question. I've got let v equal x squared z, 4 minus 2xyz minus 3y plus x squared y, 3z minus x squared z, and that's the velocity of a fluid. Now we want to compute the flux of v across the surface x squared plus y squared plus z squared equal to 25, where y is greater than 0 and the surface is oriented away from the origin. All right, so what we have here is we have a surface, okay, and we're going to want to calculate the flux around that surface. And so let's take a look at the divergence theorem, and you're going to see that the divergence theorem might be really actually quite handy here in this case. So we're going to let E, so what this says, be the simple solid region, and let S be the boundary of the surface E with a positive outward orientation. So far so good, all right, except for that simple solid region. We're going to talk about that in just a second. That's going to be our problem, the issue that we have here, okay? So we're going to let F be the vector field whose component functions have continuous partials on an open region with E. So still pretty good, except for that whole simple solid region problem, all right? If that's the case, then we have the double integral of f dot ds, right? So basically that calculation of the flux will equal now a triple integral over the volume E of div f dv, okay? So the divergence theorem is actually really handy when what you have is you have a really easily parametrizable region, okay? And and then maybe like the divergence of f is actually quite tidy and quite clean. And so consequently, what you can do if you've got this like kind of simple region, or this closed simple region, is you can then calculate your divergence, all right? Get something that's actually quite easy to integrate, and then go do that integration, all right? The problem is, and the problem with our problem here, and I'm going to show you in just a second, is that we don't actually have a closed region. We actually have an open region, or it's not solid, okay? So if we look at the surface that we're looking at here, it's x squared plus y squared plus z squared equals 25. Now that by itself is actually just a sphere of radius 5. So no problem, sphere of radius 5, no issues. But because we have the y greater than 0, that's actually going to make it so that our region is no longer closed. It's got like a hole in the bottom, right? So we no longer have a solid volume. What we have is we actually have really a surface, just a surface. So let's take a look at that. If I go in here, I'm going to draw a picture of this. Okay. And here we go. And so normally, right, okay, so here's 0, 0, 5. Okay. We have 5, 0, 0 here. We'll have over here, we've got negative 5, 0, 0. Okay. And then we'll have 0, 5, 0. And over here, we've got 0, negative 5, 0. So if this is actually the setup that we have, what we're looking at, since we know that y is greater than 0, we've got this, basically this sphere right here. But it's only a half sphere, and we actually are going to go all the way down to, we should add in 0, 0, negative 5 down here. Okay. So there we go. So we'll go down there. And so we've got that half sphere, but it's open at the back. So there's nothing in the back. It's actually opened up at the back. So that's our problem, right? Okay. So the divergence theorem by itself can't be used by itself. Okay. For this problem, what we're going to do is we're actually going to close that region. We're going to actually go in and close that region, and in closing that region, what we'll do is we'll create a solid surface. So the thing to close it is going to be a disk. We're going to use a disk, and it's this disk right here, okay? And it's the disk x squared plus z squared equals 25, right? We're going to let y equal 0, So we let y equal 0, and we get x squared plus z squared equals 25, and that's the thing that we're going to pop onto the back, and then that's going to, in fact, close our surface. Okay? Now, by the way, and we're going to talk about this in a second, that's not actually the surface that we're looking to, in fact, that's not actually the surface that we're looking for its flux over, all right? But we'll utilize that backing, right, okay, and the divergence theorem in order to then find that value for our surface, right? We're going to be kind of clever with how we do this particular problem. So what we're going to do is we're going to utilize that actual divergence theorem. So again, now what we've done is we've actually gone out and constructed a complete surface. So we're going to have a surface 1, okay, and that's f dot ds there. And we'll have a surface 2, and we'll define those in just a second, of f dot ds. And that will then equal, now that it's closed, it'll equal the divergence, okay, along the entirety of that region, div of f dot dv. Okay? Surface 1 is the one that we're actually looking for, right? That's the half hemisphere, or excuse me, it's a hemisphere, not a half hemisphere. The hemisphere, okay, above y equals 0. And then S2 is going to be that disk. That's going to be the x squared plus y squared equals 25. And so that's going to be the disk. What we're going to do, so our setup here, what it dictates for us, is we're going to actually go in here. We want to find S1. We want that hemisphere above y equals 0. That's what we're looking for, that flux there. So I'm going to subtract S2 from the divergence of f dot dv. So basically what we're going to be doing, or not basically, this is exactly what we're doing. We've got S1, the hemisphere of f dot ds, the thing that we're looking for, is going to equal this triple integral E, okay, of div of f dot dv, it's not a vector, minus the surface f dot ds. Okay. So minus, we're going to subtract out the surface integral, or that flux, over x squared plus y squared equals 25. And that's going to leave us with what we're looking for. Okay, so let's go in and do that. So let's go calculate the triple integral here. So div f dv over the region. And so what I'm going to do is first here is I'm going to calculate what the divergence of f is. So we'll take the partial with respect to x of this first term. So we get 2xz. And then we'll add to that the partial with respect to y of the second term. Okay, the partial with respect to y, so that's going to be 0 minus 2xz minus 3 plus x squared. And then plus the partial with respect to z of the third component here, which is going to be 3 minus x squared. So we've got 2xz minus 2xz, 0, 0, negative 3 plus 3, plus x squared minus x squared, so we get 0. So our divergence of f here is 0. So we don't even really need to parameterize at this point. What we'll get here is we got 0 dv, that triple integral over e of 0 dv, and that's just going to end up equaling 0. Great. So that's actually like one of the reasons why you want to use the divergence theorem, because sometimes stuff like this happens, right? Or it's like a constant, or, you know, it's like a really easy integrable function. There we are. We go out, we calculate that divergence first. And we calculate the triple integral over that divergence. Now what we need to do next is we need to calculate the flux over that second surface, the x squared plus z squared equals 25, with y equal to 0. So what we're going to do is we're going to figure out, we've got the double integral over the surface 2 of f dot ds. And if you remember that circle, that disk that we have, it's going to be oriented away from the origin. Okay, and so consequently, its normal vector is going to be going in the negative y direction, okay, or negative j. Okay, negative j is going to equal your normal vector. So what that's going to mean for us is that means we're going to have this integral, the double integral over the surface, and it's going to be f dot n, or in this case, f dot negative j ds. And that will then equal, what we'll do now is we're just going to switch this over. We're going to turn it into an area integral. And over our disk, our region, this unit disk of, in this case, let's calculate f dot negative j, which will equal, we're going to have, it's going to be x squared z, comma, 4 minus 2xyz minus 3y plus x squared y, comma, 3z minus x squared z, dotted with 0, negative 1, 0, which ends up equaling 0 plus negative 4 plus 2xyz plus 3y minus x squared z. But remember that on this region, y equals 0. So what we're going to do is we're going to substitute in y equals 0. Pardon me, I made a mistake. This should be x squared y. We're going to substitute y equals 0, and so that actually ends up giving me this to equal negative 4. So this is going to end up being negative 4, and it'll be then dA. So the derivative of our, excuse me, not the derivative of our area, but what we need are to integrate around for the area. Now, if we rewrite this, we'll get negative 4 over the region d dA. And so this is basically what this is, not basically, this is just the area of the disk. So this ends up equaling negative 4, and the area of the disk is going to be 25 pi, because all it is it's a disk with radius 5, right? So pi r squared times 5 squared times pi, and that equals negative 100 pi. Okay? And so that's actually the flux over that region. Okay, so now we've gone in, we calculated the flux over that region, we calculated its surface integral. So now remember, our region, S1, of f dot ds, so the flux over that region, is going to equal this divergence of div f dv minus the second one, S1 f dot ds. And so consequently, this is going to equal 0 minus a negative 100 pi, which just simply equals 100 pi. So what we've done here is we've basically gone in and we closed the region. And by closing the region, what we've allowed us to do is to actually utilize the divergence theorem, because this divergence is really simple, right? It actually zeroes out. And the second surface that we needed to close the region was actually a pretty simple integral as well, making it much more simple to calculate here the surface integral over the top of that hemisphere.